Welcome to calculus.
We've always been good at math. How hard could calculus be?
On this episode, Stevenson will demonstrate
Let's now use our second derivative knowledge. So this first example here says, use the concavity test to determine the concavity of a given function on the given intervals. So here's my first example. I have y equals x squared on the open interval from 3 to 0. So we're going to try to figure out what the concavity is without looking at the graph. Well, we're going to use the second derivative, so let's find that first. Okay, let's look at what this graph looks like. So this is the graph of my second derivative. It's just a constant line going through y equals 2. Well, notice this function is always positive. Remember, according to the concavity test, if the second derivative is positive, that means the function is concave up over that interval. Well, this graph is always positive, it's constant. What this tells us is this graph is concave up on the entire interval from 3 to 10. Now, we could have figured that out without doing any second derivatives. How could we have figured that out? Well, isn't this just the parent quadratic function? Right? Isn't the whole thing just concave up? So yeah, so we expected this answer. Let's look at another problem. So again, we're trying to find the concavity of this function on this particular interval. Is it concave up? Is it concave down? And we're going to use the second derivative to do that. So step 1, find the second derivative. Step 2, let's graph our second derivative, because what we want to know is look and see when is it positive, when is it negative. Now, I'm only interested in the interval from 0 to 2 pi. And because this is a negative 1 in front, we're going to take our regular sine graph, which starts at the origin and then goes up, and we're going to reflect it. But remember, we don't want the sine graph, we want the negative of sine. So the negative in front reflects this. So all these points will reflect over the x-axis. Now let's make a sign chart because we can see that our second derivative actually alternates sign. It's negative and positive. So what am I going to put on here? Well, I'm going to focus on this open interval from 0 to 2 pi. And I want to note the x-intercept here. Now, this x-intercept, now keep in mind, this is when the second derivative is 0, which means this is a candidate for a point of inflection. Well, how do I know if it's actually a point of inflection? Well, let's look at the second derivative. On the interval from 0 to pi, the graph is below the x-axis, so it is negative. And from pi to 2 pi, it is above the x-axis, which means it's positive. So we know that pi has to be a point of inflection because the second derivative changed sign. It doesn't matter how it changes. So now we know it does in fact change concavity here. So let's write out a statement. So we're going to say the function y is concave up on the interval from pi to 2 pi, the open interval from pi to 2 pi, because the second derivative is positive. Now, y is concave down over the open interval from 0 to pi because the second derivative is negative.